Hi everyone, welcome back to On the Spot STEM. Today we'll be doing day 2 of the 30-day LeetCode challenge. So this problem name is happy number, and the problem reads, write an algorithm to determine if a number is happy. A happy number is a number defined by the following process. Starting with any positive integers, replace the number by the sum of the squares of its digits, and repeat the process until the number equals 1, where it will stay or it loops endlessly in a cycle which does not include 1. Those numbers for which this process ends in 1 are happy numbers. And so our example input takes 19. We take the sum of the squares, which is 1 squared plus 9 squared, which is 82. Then 8 squared plus 2 squared is 68. 6 squared plus 8 squared equals 100. And then 1 squared plus 0 squared plus 0 squared is 1, in which case this would terminate. So basically, our problem just tells us that our problem basically confirms for us that we have two sorts of cases. We either go from our starting case n, and then after we do our square function of n, let's just go to some other number. I'll just put this at a circle. We don't know what this number will be. Then we'll go to another number, we'll go to another number, and so on. And basically, one state is where we can reach 1, or the other scenario is that we go to these numbers, and at some intermediate point in this process, we'll reach another number, which will then cycle back. So then we'll go here, then here, then here, and then we'll cycle back to one of these numbers, and then this will be stuck in this type of cycle forever, in which case our output should be false. So we have to find a way to distinguish whether we're in a cycle or not. And basically, the easiest way to do this is to keep two counters. And basically, we can just model these as steps. So each time we find the sum of the squares, that's taking one step. So the nice thing about keeping two counters is, if we make one counter, let's call this the fast counter, goes 2 steps at a time, and then we have a slow counter that goes 1 step at a time. Basically, if our slow counter or fast counter will reach 1, or if any of those two reach 1, then we know we're done, because that means after some time, after like a bunch of times that we iterated it, we'll reach 1, so we know that's true. But once we're in a cycle, since both of these counters are still going a finite amount of steps, that means once they enter a cycle, they can't leave the cycle. So our fast one will probably enter the cycle first, so it'll jump around here, it'll jump out like 2 at a time, and then so on. And our slow one will go like only 1 at a time. And if they're both in a cycle, that means if a fast counter is taking 2 steps and the slow one is taking 1 step, that means essentially the fast one is catching up by 1 at each point. So that means after a finite amount of points, or just a cycle length, the fast one will reach the slow counter. And if the fast counter is equal to the slow counter, then we're basically done, because we know it's in a cycle. Because if it wasn't in a cycle, then the fast one would reach 1 early, and it would never be the same as the slow counter. So once they're equal, that means we can terminate and say they're false, but if they reach 1, then we can terminate and say it's true. So over here is the code for this problem. Basically, we had to implement this Boolean function as part of the problem. To do that, I made a helper function, which is square, which just takes n, and this part over here is just taking n mod 10 and multiplying it by itself to get the sum of the squares of the last digit, and then you divide by 10 to chop off the last digit and so on. And then this part, we have the slow thing, we have the fast thing, our fast counter, and then while our slow is not equal to fast, we basically go 1 step for slow. This is going 1 step, and for fast, we increment it by 2 steps. And if our slow is equal to fast, then we're going to be done. We'll just return whether slow is 1. But otherwise, if it's equal to 1, then we can also say it's true. So now I'll run and submit it. So as you can see over here, our runtime beat 100% of Java submissions. So it means that we basically found the fastest possible solution to the problem, and also the correct solution to the problem. Thank you for watching. If you enjoyed this video, please don't forget to like and subscribe. And we'll be doing this every day for the 30-day challenge, so stay tuned for day 3 and so on if you're interested in this. Thank you.